Alright, hell yeah, statics. Alright, for engineers, here we go. Now, this problem I was just thinking, we could just kick it out and just find the units. I mean, you have moment of inertia, and you have mass, that's in kilograms, radius is in meters squared. So it looks like the units are kilograms meters squared. You know what I mean? So how do you do a problem real fast? You just attack it just like that. And so we know that kilogram is a capital M mass, meters is a capital L length squared. So there you go. We just did it. And like I said, anytime you get these FLT, MLT, write F equals MA. And if we're pro at it, we can be like, hey, this is capital F, capital M. A is meters per second squared. So that's going to be capital L divided by T squared. Okay, and then just rearrange, solve for M. So you got M, T's go upstairs, so F T squared over L. Okay, and now all you got to do is just substitute this in. And then we're going to talk about the MLT, FLT. But I was just like, might as well do it in this order first. So now we have F T squared. You got that L squared divided by L. One of these L's cancel, and you got F T squared L. Alright, booyah. And this problem's in the back of the book, you know what I mean? Maybe we made an error, you know what I mean? I don't know, but I don't think so. You got mass, length squared, that looks pretty golden. And then you just, as long as we didn't mess this up, you know what I mean? You got the force, only one L, and then T squared up top. Alright, so let's look at the answer in the back of the book, just to make sure we can move on. But then we'll talk about this, because, yeah, it's super exciting. I should have talked about it first, because now I think I just forgot what the hell I was even doing. Did we get it right? So we have ML squared, got that one, and then the FT squared over L. We just did in reverse order. So this is your force, length, time. This is the gravitational system, and then this is the mass system, obviously, because you're putting the mass in there. Alright, so hell yeah. So now, I almost kind of forgot what I was doing, but I at least read in the books, just like, you know what I mean? This is the gravitational system, and it's not absolute. It's based on your position. So if you're on the Earth, the gravity is constant, you know what I mean? And the force that you weigh in weight is going to be the same no matter you're on Everest or like the deepest part of the ocean. In that region, you know what I mean? You're not too far away. Okay, now I'm refreshing my memory. So this mass, length, time system is totally absolute. You know what I mean? We're just clumps of molecules, and we're just saying that, hey, if you add up the number of molecules, you know what I mean, that's going to be a property of mass. You know what I mean? That ain't going to change. Whether you take those molecules to the moon or wherever, Mars, it doesn't change. Black hole, it's not going to change the number of molecules that your system comprised of. All right, so this gets me thinking that, we have this equation that says force is equal to mass times acceleration. No, is the gravity. Gravity is usually just like, just given. Hey, this is 9.81 meters per second squared. Or gravity is 32.2 meters per second squared. You know what I mean? And there's a lot of equations that involve, gravity as part of part of solving the problem. But this this number essentially comes from, the force of gravity, gravitational constant, mass 1, mass 2, radius squared. So even if you have a person that jumps off of a building, you know what I mean, and then, or I don't know, that's kind of or a rock or whatever. I don't know, maybe there's a pool of water and it's not so devastating, you know what I mean. But anyway, you have this Earth, and this Earth has a ton of mass, and you have mass, and there's going to be this attraction between you that's dependent on your distance. You know what I mean? So as you get closer to the Earth, this changes. You know what I mean? So just know that you can always you know, any time it's suspect, anytime that you see, hey, they're giving you the gravitational constant, well, cool, but it only works for that limited. You know, the second you start taking a spaceship up out of this zone, your gravity is not at all 9.8. You know what I mean? And so I don't know. You know, International Space Station. You know, what's the force of gravity? The International Space Station. I don't even know how high that thing is. But anyway, I guess that's all I was going to do on that. But you can just, at the end of the day, well, I guess let's take this. We got 2 sheets of paper. So you got F equals ma. People are saying that gravity is 9.81. And that's just this part of the equation. And then you have this Kepler, Gmm over r squared. So F equals ma, what we do is we measure a force with a scale, or we see an acceleration over here. We measure the force on the scale, and we know that, so this part gets is over here, so Gmm over r squared is equal to the same mass, and we're going to see it fall, you know what I mean? Because we're going to see a rock fall or whatever. And these masses cancel, and now you have, and we'll rearrange the equation, Gm r squared. So this is the mass of the Earth. Well, that ain't changing. Gravitational constant. Well, by definition, a constant ain't changing. And that's cool that we haven't found, you know, other places where that gravitational constant isn't the same number. But this radius from between the 2 masses, you know what I mean? So you have little m, and then you have the Earth at the center. That's the big M. That distance between the center of the Earth and the center of you, it is changing. You know what I mean? Whether you pop up into an airplane or, you know, get to travel to the International Space Station. You know what I mean? And so just know that anytime someone gives you 9.81, it's because of this. It's because of this equation, you know what I mean? So you could just throw this equation in instead of 9.81. Throw this equation in because your distances might change, and that's going to change your force. There's plenty of problems, you know what I mean? Whether you're sliding down a ramp and then you hit a frictional, you know, patch, is where you're just like, you know, from here to here, you have an average force. But then from here to here, you have a force average of friction. Right here you have a force average of gravity. You know what I mean? But this gravitational force actually changes because you're getting closer to the center of the Earth. So, you know what I mean? Obviously, any problem that involves anything on the Earth or near the surface, it always 9.81 is probably going to be good enough. That ain't going to change, but just from a physical perspective, you should know that does change whether you go up into an airplane. An airplane's high enough where this gravity changes. It's 5 miles up or whatever. 7 miles? Who knows? And you will weigh less. I've always wanted to do that. Take a scale, weigh myself before getting on the plane, and then, you know what I mean, when I can walk around the cabin, weigh myself there, and hopefully I didn't dehydrate myself or anything. Hopefully that's only a 30 minute between, you know, on the ground and where I can measure myself in the air. That would be pretty cool. I guess you have to wait halfway through the flight to actually get up there. Who knows? But anyway, just keep that in mind. That's all. That's all. And if we use the MLT system, we're not relying on just someone giving us a number. You know, we're working with the mass of the Earth. We're working with our mass. Those don't change. And we can always figure out our radius between us. You know what I mean? But still, now we have an absolute an equation of what that force is going to be. It's not just a number that magically changes if we get farther away from the Earth and we're just like, what the hell? Anyway, all right, so that's enough rambling for that one. Thanks for joining me, and guess what? That's a video.